Now that you've been working with the normal distribution for a while, I'd like to go back and sort of put some things into perspective and make sure that you understand the basic nature of the normal distribution and particularly how we're going to use it to calculate probabilities that we're interested in. The most basic thing that you can know about the normal distribution is that it is a bell-shaped curve, and it's always symmetric about its mean mu, and the total area under the curve is always 1. In addition, the shape of a normal curve is always completely determined by its mu, its mean, and its sigma, its standard deviation. If you know the mean and standard deviation of a normal random variable, you know exactly what the normal curve associated with that random variable looks like. I've exaggerated some of these things here just to make a point, but given a certain value of mu, the only way the curve can vary is in its standard deviation. A small standard deviation, say of a half, has a curve that hugs the mean more closely. As the standard deviation gets larger, the curve spreads out farther and farther in the tails. In this course, one of our main reasons for studying the normal distribution is to use it to calculate probabilities. And in order to do that, one of the skills we're going to have to develop and enhance is the skill of finding the area underneath the normal curve between two different values. And the reason we need that is because these areas are going to represent probabilities of things that we're interested in calculating. There is somewhat of a problem, though, but we're going to solve it, and that is, how can you have a table to look these things up in if you could have varying means and standard deviations? As we said earlier, a normal curve is completely determined by its mean and standard deviation, but if you've got one problem with a mean of 5 and a standard deviation of 2, and another problem with a mean of 0.7 and a standard deviation of 1.62, you're going to have a table for every possible combination of those, and that's simply not possible. There is a way around that, and that's what I want to talk about now. Of course, you've seen this already, so you know what I'm going to say. The trick, the way around this, is to standardize our normal random variable. And the way you do that is you take the normal random variable, call it x, subtract off its mean, and divide by its standard deviation. If you do that, you get a new random variable, which we typically call z, and that is the standard normal random variable. In other words, z is distributed as a normal distribution with a mean of 0, mu is 0 for a standard normal, and the standard deviation is always 1. So if we can standardize our variables before we try to look them up in the table, then we'll always be looking them up in the z table, in other words, the standard normal table, and that takes an infinite number of possibilities for tables which we cannot deal with, and reduces it down to always looking it up in one table. So if we can take a normal random variable, subtract off its mean, divide by its standard deviation, we will have the standard normal, which always has a mean of 0 and a standard deviation of 1, and we can table those values, and in fact those are the values that are tabled in the back of your book. And just to point this out once again, as for any normal curve, the total area underneath is always 1. And because the normal distribution is always symmetric about its mean, half of the area will always lie to the left of the mean, and of course the other half of the area will lie to the right of the mean. How does this all apply to the table in the back of the book? Here's the connection. If you want to know the area underneath the standard normal curve from a certain value of z back to the left, that is what is tabled in your standard normal table. In other words, if I wanted to know the area under the standard normal to the left of z equals 1.1, I would go to the table in the back of the book, look up 1.1 for z, go into the body of the table, find that value, and that decimal value would represent the area to the left of that 1.1. So that's the connection. The table in the back of the book gives you that area in green for any value of z. Of course, if z is very large, you're going to get a large area. If z is actually negatively large but small, going to the left, then the area is going to be correspondingly smaller. So as z gets larger and larger and larger, the area under the curve gets closer to 1. Of course, by now you've probably done enough of these problems that you'll realize that we're not always looking for the area to the left of something. We might, for instance, want to know the area to the right of something. If I wanted to know the area to the right of, say, z equals 1.1, I would go to the table, look up 1.1, find this area, and since the entire area is 1, I just say 1 minus. So if I want an area to the left, I just look it up in the table. If I want an area to the right, I look the number up in the table for the left, subtract it from 1, that gives me the value on the right. The other possibility is, and it happens quite often, is that I actually want the value between two values. I might have a value here and a value here. How would you do that? Well, it's easy, but it is something you need to think about. Let's look at that. Suppose you have a particular value z, and I don't want to specify it, so let's just call it a. And I know how to look that up in the table. I go to the table, cross-reference that value z, go into the body of the table, that gives me the area. If I have another z value that I'm interested in, let's call it b, and let's say b is larger than a, I go to the table, look up my b value, that gives me the green area here. But like I said, I'm not really interested in the area to the left of either of these. I want to know the area between a and b. In other words, I want this area right here. How would I get that? Once you see it laid out this way, it's probably pretty obvious what you do. If you go to the table and look up this value of z, whatever it happens to be, 1.1 say, you get a fractional value less than 1, and that represents this area in green up top. Think of that as being here, and say it even runs underneath this. It's the area from B to the left. Then this table value of A is the area I've drawn here in red, and it's determined by looking at this value in the table, finding out that fractional value in the table. If you think about this red as being like subtraction, if you put this on top of this big green one, you'll knock off some of the area, and as you can see, what's left is exactly what I'm looking for, namely I'm looking for the area between A and B, and if I take off this much of the area that was in green, what I'm left with is exactly the area between A and B under that normal curve. So the trick is, if you want to call it a trick, if you want to look up value, the area between two values using standard normal table in the back of your book, you look up the value associated with the largest z value in the table. Then you look up in the table the value associated with a smaller z value, and you subtract the two table entries, and the remaining difference is the area underneath the curve between A and B. If you think about it, that really explains what you've already been doing, but let's take this sort of explanation of how that works and apply it to some real problems.